tons of old friends that I have here. Hiding the American flag. I hope it's okay in this day. Okay, so what I'm going to do is give half Blackboard, half PowerPoint talk, basically try to exemplify some of the things that Jen was speaking about yesterday. And of course, this is not really work done by me, it's done by the people in the first row. So, and Luis Alcoro, who is at dealing with the Bilbao crystallographic server. Okay, so the option that, the viewpoint that we're going to adopt in this talk, which is a viewpoint kind of inherent in all the topological phases, is that a topological state cannot be, or a topological set of bands cannot be expressed as in terms of just localized orbitals. So if you look, I'm just going to go through it very fast, through this argument very fast, because it's a hand-waving argument right now at this level of the slide, but it's a very concrete argument that we're going to use to build the phases that we're going to build on the board. So basically, we know, and it was clearly shown in Jen's talk, that if you have a non-trivial insulator given here by some integer c, which has value 1 in this case, sitting next to an atomic limit insulator, and this is atomic limit, meaning in this case, which is not entirely correct, but in this case, the atomic limit is the limit where I take the atoms and I push them to infinity. So no hopping between the atoms, 0 hopping. And this has to be a trivial state. So I have some SMP orbitals on each side and no hopping. And the system is going to want to occupy the orbital with lowest energy. And it's an insulator, the most trivial insulator. Sitting close to a non-trivial insulator with some symmetries, you're going to have, if the boundary does not break those symmetries, you're going to have a gapless region of edge modes on the boundary. And that's enough to basically tell you, so this is kind of the bulk edge correspondence, and this region of gapless edge modes that has to be there is enough to basically tell you that while this side can be described by localized orbitals, because I'm just occupying every orbital that's got a low energy, this side can never be expressed just in terms of localized orbitals. And one way to understand it is that, if you look in this whole system, there is on the edge a region with power law correlations. And if these are just delta functions here, so or exponential correlation, so if I can describe this ground state by exponential decaying orbitals, then I won't be able to get some power law correlations such as a region of gapless edge states. So these are basically the extended states, the manifestation of the extended states that live in this bulk region of a non-trivial insulator. There's some extended states here, which means non-exponential, and some potential at the edge makes them raise up and cross the Fermi level. It's the same thing as in the quantum Hall effect. Okay, so that's going to be the motto of the talk. And as Jen explained, basically the moral of the story of this, of how we're going to think about topological phases, is we're going to build all the phases, or we're going to build all the band structures that are trivial. And everything that's not trivial has to be, by definition, topological. So we're going to build all the phases that are trivial. And while there has been a lot of work on this in the literature, this is actually an old problem. And while we did the full classification of it only recently, the idea of building the atomic limits, just the phases that can be represented by atomic orbitals, by localized orbitals, belongs to Zach, and Zach, Bakre, and Michel in the 1980s and the 1990s. And they were very close to, at least conceptually, to discovering topological insulators. If, probably if Bakre or Michel or both of them didn't die, they would have found topological insulators. But basically, they didn't completely classify them, but they had the idea of how to build all the atomic limits possible. And all the atomic limits possible are the elementary band representations that Jen was talking about. And I'm going to skim very fast through these and then show you how to build one. So basically, like not go through what Jen went through, but kind of try to complement it by showing you a specific example. So just skimming very fast through what Jen went through, this building elementary band representations basically starts, since you're building atomic limits, you start from atomic orbitals on sites. And this is a honeycomb lattice, and I start with SRP orbitals. And Zach had the idea of looking at, not the full space group of the lattice, which is C6V plus translations, so 2 pi over 6 rotations, mirror, and some translations. But instead of, if you want to build atomic limits, you look at where the atoms sit, and where the atoms sit, they fill a different space group, or a different point group than the point group of the lattice. For example, if the atoms sit here, they don't feel this environment here is not C6 symmetric, it's not 2 pi over 6 symmetric, it's only C3 symmetric, and they feel a C3 potential. So really, my representations, the way I should describe my orbitals are representations. They're no longer representations of the full rotation group, like SO3, but they're representations of this side symmetry group here. In this case, this side symmetry group is C3V, right? It's got C3 rotation, because it sits here, C3 rotation, and mirror, this mirror, for example. And it turns out that there's a theorem that you can build the full space group as a coset decomposition of this into a coset decomposition with the coset representatives not belonging to the side symmetry group, which is this guy here. So for example, I can build my full space group as the side symmetry group, which is C3V, times translations, semi-direct product, times the coset representatives, G alpha, where G alpha, with the exception of the identity element, there's an identity element, all the other, so G1 is the identity element, all the other G alphas do not belong to this side symmetry group. So we're going to go through that, and then we're going to exemplify. So for example, here I have so again, the side symmetry group that leaves this site invariant is C3V, and you can see it that is C3V because C3 takes this to this, but up to a translation, this is the same. So I have to, instead of taking C3 element, I take the C3 element and the translation by the second lattice vector, right? So this leaves the site invariant. So this element is in the site symmetry group of this site. This leaves the site invariant, this element mirror, okay, times no translations. So this mirror, this is the mirror line, times no translations leave the site invariant. So these two elements leave the site invariant plus the identity. They form a C3V group, isomorphic. It's not really it's not the usual C3 that you know, but it's isomorphic to C3. The only difference is this translation here, okay? But there's another element, which is, you can think of it as C6 if you want, but here it's thought as C2. C2 belongs to C6V, right? This full lattice has C2 symmetry because this moves here, but it doesn't belong to the side symmetry group because C2 sends this side into this side, and this translation is not a multiple of translations. Okay, so C2 does not belong to the side symmetry group, but it belongs to the coset representatives. So, for example, I can, there's two alphas, two G alphas here, the coset representative. One G alpha is the identity, and the other G alpha is the C2. Okay, and then I can form the full coset decomposition of the space group in terms of the coset representatives, the side symmetry group, and the translations. And then the orbitals that live here are basically some representation of C3V. So if I don't have mirror symmetry in plane, for example, like this, in the z direction, so this z going to minus z, then S and PZ orbitals are the same. Okay? And you classify your orbitals here by the representations of the side symmetry group. Okay? So now, why did I use this coset decomposition? Well, the reason why I use this coset decomposition is because Zach made this fundamental observation that you can think of bands as representation inductions. So basically, Zach, I guess, was looking at math. And in math, you're trying to, you have a large group, and you try to find representations of a large group. And that's usually very hard, and usually the way people do it is to look at subgroups of that group, find representations of subgroups, and then do what's called induction. Okay, so you take a representation of a subgroup, and you induce it to the full space group, or to the full group. You take a representation of a subgroup, and you induce it to the full group. And this is a procedure called, is basically induced representation. It was, I guess, invented by Frobenius a long time ago. Okay, so Zach basically then said the following: if I want to find the atomic limits, he didn't call them atomic limits, but this is what they really are, because I'm starting from orbitals. All I need to do is take a representation of a site symmetry group and induce it into the full space group. Because the site symmetry group is a subgroup of the space group, right? I gave you the Coset decomposition. So Zach said, I'll think of bands just induced from orbitals as just inductions of representations from a small group, the site symmetry group, which is the point group, to the big group, which is the space group. Okay? So I'm not going to go through the full theory because I'm going to show you an actual example. But it turns out that, what Barry, Jen, Zijun, etc., and ourselves did was basically to classify all of these. So it turns out so now you go through some formalism, and you end up with some statement that all elementary band representations can be induced from irreducible representation of the maximal site symmetry groups. The vice versa is not true. There's a list of quantifiable exceptions that's complete that you can find it in our paper. But the point is, what is this? Let's parse this statement. So what does this statement mean? Well, it means that first of all, you have these bands, which Zach said are induced representations from the site symmetry group representation to the full space group. What are these bands? They're atomic limits of some orbitals living on this lattice. I have no Hamiltonian yet. But then you can ask several questions. So normally when we have a representation, the first thing we ask is this representation reducible or irreducible? And the statement here is basically that elementary band representations are the equivalent of irreducible representations for bands. Okay? So basically, you induce this representation for the site symmetry group into the full space group, and then you ask, can I break it up into smaller bands? So it's a band called band representation. Can I break it up into smaller bands? And it turns out there's a minimal set of bands that you can break, which are called elementary band representations. And these are induced from irreducible representations of these sites. Now, which sites I induce from? That's another question that you can ask in the lattice. Well, it turns out I can put orbitals. Yes, sorry, there was a question.
So what does it mean to induce something from a representation?
Yeah, that's a good question. I'll go through that. I'll build it on board. Yeah, because that's very abstract. I'll just build just 3 minutes, and I'll build it on board. Or 4 minutes. Thank you. I'm just giving you the gist of what's okay. So of why these are countable. Okay, so it turns yes.
Naive question maybe. Aren't these all these irreducible representations that subgroups are tabulated already?
They're tabulated on the Bilbao crystallographic server, all of them, yeah. I mean, their Berry phases are not tabulated, but something about them. The high symmetry point representations are all tabulated. Okay, so the reason why it's so Jen gave this number 10,000. So the reason why it's quantifiable is the following. Normally on a lattice, I can put things, I can put orbitals wherever I want to, as long as it respects the symmetry group, right? So I could, there's an infinity really of spots on the lattice, right? I can put an orbital here, like in graphene. I can put an orbital here, like the lower bands of graphene. I can put an orbital here, 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 here. Of course, I would have to put orbitals wherever the symmetry, acting on the symmetry, but there's an infinite space. There's an infinite space of positions where I can put an orbitals at unit cell. So how do I know that this, I can have an atomic limit from each of these orbitals? So how do I know this quantifiable? Well, this is where maximal site symmetry groups become important. It turns out that not all the positions, some positions are better than others, not all the positions are democratic. So basically, these positions, which are not maximal, the bands that are induced from these positions, so if I put an orbital here, which I have to put one here, 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 the bands that are induced from these positions could be decomposed into elementary bands induced from this position or from this position. Okay? And which one of these positions you pick is in the list of these quantifiable exceptions. Okay? But the point is, only maximal site symmetry groups are important, and maximal site symmetry groups basically means that the site symmetry group here, there's nothing between this site symmetry group and, in this case, the point group of the space group. So for example, you see, this point is C3V. There's no other subgroup between C3V and C6V. This point has a site symmetry group C6V. There's no other subgroup between C6V and C6V. But this point here has lower symmetry, it's just C2 really, and between the site symmetry, between this and C6V, between the symmetry group, site symmetry group of this guy and C6V, there's obviously this guy, which is C3V, right? Because there's a line of parameters, so I can go here. This site symmetry group has to be a subgroup of this guy and of this guy. Okay, so this is not a maximal site symmetry point. These are maximals because there's no, these are related to maximal and non-maximal Wyckoff positions, but you don't have to think about that. Basically, the point is that if I try to induce, if I induce a band from orbitals sitting here, I can decompose it into bands induced from orbitals sitting here. So this band representation is reducible, and this one is not, for example. So this basically tells you the fact that you can only induce from maximal Wyckoff position. It tells you that you have a quantifiable set of elementary band representations. And you can think of these 10,000 as 230 space groups times around 5 Wyckoff positions, roughly on average on a lattice. There's 1,000 times 10 representations per point group, say, roughly. So there's 10,000, or of that order. Okay, so this is the expression of how you induce a band representation, which I'm not going to take you through, but it's an actual expression that has, so I'm not going to take you through because I'm going to take you through an example, so you don't have to look at it. But basically, this is a group, this is a representation, this is the space group, this is a representation of the site symmetry group, this is the induction symbol, you induce it here, and then this is the expression, okay? So you have, you can Fourier transform it, so you have a momentum here. T alpha beta is, this quantity, and you have this group element G alpha beta has to belong to the site symmetry group because this, you see this row here on the right side is this row. This row here on the left side is this row, okay? So this guy has to belong to the site symmetry group because I'm only defining representations of the site symmetry group, and I induce them to the full symmetry space group, and this is the one thing you get is a phase plus some, for every element of the space group, you have to find by the coset decomposition the element of the site symmetry group that it corresponds to, and then you apply this formula and you have an induced representation. But I'm going to go through it, so don't worry about it. Okay, so that being said, let's just do an induced representation. And related to Berry phases. So the first thing we're going to do is one dimension. Is this big enough? Okay. So one dimension, and the simplest symmetry that we're going to take is inversion, and that's all we're going to do, but it should be pretty obvious that this is generalizable to everything. So inversion symmetry, okay. And I'm going to take the system with one site per unit cell, but I'm going to go to two orbitals in the end to make connection to insulators because I need. But so far, I'm just taking one site per unit cell, so I'm just taking, these are the sites. These are where the atoms sit. Of course, charge can move in between the atoms, right? This being quantum mechanical, but that's where the atoms sit. This is my lattice, okay? Now you pick an origin, always pick an origin of the lattice, which you cannot change afterwards. So I pick this origin, Okay? And now I ask, are there some special points in my unit cell? And how do I classify these special points in my unit cell? And by what we've done here, I look for points in my unit cell that have a group that leaves them invariant. Yeah? So is this point special? Call it 1A. In crystallographic language, is the 1A Wyckoff position. Is this point special? Why? What's the site symmetry group of 1A? It's the inversion, yeah. Exactly. It's inversion plus 0 translation. So I'm going to put it like this, right? Okay. Okay, very good. So now we don't go further. We just, what are the representations of this site of this? So we said that what we do now is we put orbitals on the site. What are representations of this site symmetry group? So in terms of orbitals, there's two representations, which are this G is identity and inversion. But I'm not gonna, okay? I'll always delete identity. I'll always delete identity. If I got it. Thank you. Thanks. Okay, so what are the site symmetry? What are the representations of this of inversion? There's two of them. S and P. So S representation with eigenvalue what? Plus and plus 1. And P representation, and it doesn't matter in this group if it's Px, Py, or Pz so far, with eigenvalue what? Okay, and I'm going to call them S1a and P1a. Can people from the back still see? Okay, so I'm going to call them S1a and P1a because they're on this site symmetry group. Okay, but there's another in the unit cell. There's another point that's also special, which is which one? This is one that Jen was showing in her SSH example, which is this one. Of course, there's translations, right? If I pick my origin here, this one would be, and it doesn't matter. I just first build it here and stuff. So this one is also special, and you call it 1B, Wyckoff position. And what's 1B in the? What's the site symmetry group of this guy? Well, inversion takes me here, but then I have to so it's inversion times Tx, right? This is isomorphic to inversion, right? It still squares to 1. This as a group is the same, but it has this thing, which will become important when I induce a representation to momentum space. Okay? This is, for example, this is this guy. You see? H times Q alpha. Q alpha is 1/2. This guy, this 1B Q, this is Q, for example. So H inversion times Q sends it here. Okay? Minus Q is exactly this Tx. You see? This is this factor. Because I have inversion times 1/2 is equal to minus 1/2 minus another 1/2. It's exactly 1 Tx. Okay? So that's that factor. So now I have on site, on this here I don't have any orbitals, but my center of charge can move here. So what are the representations of this site symmetry group? Abstractly, they're also S with eigenvalue what? In real space. And P with eigenvalues, yes? -1, right? Does that make sense so far? It doesn't make sense. If it doesn't make sense, then tell me what doesn't make sense. What does what? The paperclip. Which one? This thing. This is inversion plus a translation. Sorry. But this translation is by 0. You see here, to keep this site invariant, what are the symmetries that keep this site invariant? Inversion. But since it's at 0, I don't need to do any translation. Yeah? But this guy here, the site symmetry group of this position, is inversion. Inversion sends me here. I have to translate by 1 unit cell. So inversion times dx. Does that make sense now? So now, okay, so now everything is clear. Right. So here, I'm saying what type of orbitals. So you know, now we have to add orbitals. What types of orbitals? I'm just classifying all types of orbitals by representation that I can add on this side, or that I can add, quote unquote, because there's no site here, but the center of charge can move here, and it has to be in real space. It can be in a representation of S or P, also, right? Because this group is isomorphic to inversion. Just the eigenvalues are just how I classify. There's 2 representations, S and P, and they're classified by the eigenvalues under inversion, under this inversion. And here they're classified by the eigenvalues under inversion times Tx. You know, if I have Px, for example, if I have Px at 1b, okay, inversion takes it to plus minus here, but Tx moves it back here, and I have minus plus, so it's exactly minus. Is everything clear now? Perfect. To everyone? Fantastic. Okay, good. So, okay. So now the fundamental thing is, now you're asking, so these are, so now we're going to ask what kind of bands can I get in momentum space from these orbitals in real space being tiled in this, right? So if I have an orbital here, an s orbital here, then I have an s orbital here and here and here and here, okay? And all I need to do is apply this formula to find the representation in momentum space, yeah? And this formula is just the following. Here, this formula, so rho g, and I'm only going to put, I only want the matrix element inversion here, the group element inversion here, because identity is always 1, okay? So I'm going to ask, what does S1A induce into the full space group, G, which is inversion, translations, and identity? Okay, I'm going to ask, what is this band? Well, this is a band that's induced from s orbitals into sitting on every position 1a of the lattice into the full space group. And this band representation is going to be just, so it's just going to be, because you see, there's no translation here. There's no translation here, so this thing would be 0, okay? Or in other words, this q for 1a, this q is 0, okay? So t beta, t alpha alpha is h q alpha minus q alpha, 0 minus 0. So this guy is just going to be S1a, the representation. Okay, so I call these are the representations. P1a induced into G is just P1a, because they're induced from with no translation. Here, the situation is very different. S1b induced into G is equal to S1b, but I now have a phase e to the minus ik tx, yeah? Because the representation of this guy in momentum space is e to the ik. Right? So e to the minus ik x. There's only one k, really. So, but we're going to go to 2 dimensions. Right? So this is the, if I have an orbital at 1b in momentum space, it's going to induce a band whose representation is e to the minus ikx times this site symmetry representation. Just because I had this factor. If you want to think of it heuristically without applying this formula, you can think of this e to the ikx as the representation of tx in momentum space. Yes? Okay, so then can you tell me what P1b induced into G? This is a band representation. These are just atomic limits. So this is the atomic limit coming from s orbitals. So this is the atomic limit coming from p orbitals. So this, etc. Can you tell me what this is, please? Times? Very good. Okay, so now I claim that we have all the atomic limits all the elementary band representations possible in this 1D lattice with this simple space group. Why? Because we have identified all the maximal Wyckoff positions. Another Wyckoff position where I could have an atom is here, say somewhere at some arbitrary thing, okay? But this guy, you know, and if I have one here, I'll have one here also by inversion. But this guy is not maximal, okay? Because, you know, this symmetry group is included into the symmetry group of this guy, for example, right? So the side symmetry group of this guy is just identity. There's no special side symmetry group of this guy. So actually what happens if I have orbitals here, I'll have one here, I can decompose them into orbitals that come from here or from here. And this is SP hybridization, which we'll see in 5 minutes. Okay, so is this clear? These are the band representations. That's how you build them. And now it should be clear that you can do this for every space group, really, algorithmically. Well, algorithmically, you can do it explicitly. Okay, so now what's important about these? Well, what's important is that now you can go to the Brion zone, and you ask what are the eigenvalues of these bands? So these are bands, okay? Their energetics might do this, okay? Or might do this, or might do some other stuff. I don't care. These are actually the universal properties of the bands. I describe them by this representation. How they look as a function of momentum, energetically, you don't care about. That's something that this theory cannot give you. So now you go to the Brion zone. And what this now gives you is immediately all the eigenvalues of all the atomic limits at high symmetry points. Right? That's the first thing it gives you. So how? Let's see. Well, the S11A induced into G, let's just make a this is the point 0 in the Brion zone. This is the point pi. They're important because that the little group here and here is inversion. Yeah? Inversion keeps these points invariant. So I'm going to try to find the eigenvalues of these bands at these high symmetry points in the Brion zone. So the band induced by S1 by the orbital S by the orbital S at 1a induced into G has what eigenvalues at 0 and what eigenvalues at pi. So it has no phase factor. And what's the eigenvalue of S1a? Plus. So because it has no phase factor in the Brion zone, what is it here? And what is it here? Perfect. P1a induced into the space group, what are the eigenvalues? Minus, minus. Now, S1b induced into the Brion zone, into the space group, and Fourier transform to the Brion zone is what now? What? Plus minus, because e to the ik pi is minus. And P1b is minus plus. Very good. So now we found all the atomic limits. These is, well, all the universal properties of the atomic limits, okay, which are just the symmetry properties. In fact, we know a little bit more than the eigenvalues, but here it won't be relevant. We know a little bit more than the eigenvalues because we know the full dependence, and this is the Berry phase that will become important in higher dimensions. But so far, we know the full dependence of the induced representation. So we know how it parallel transports, for example, in momentum space as e to the ikx. But this is a very simple group, so it won't matter for this. Okay? But we know. I just wanted to point out that we know more because we know these. And generically, you'll know these from here. Okay. So now, I want to point out something and relate this to what Jen was saying about Berry phases. So we're going to try to find out the Berry phase structure of all these bands. Okay? just to relate to something physical. So the first thing that I wanted to point out, that you'll have to remember later, is that in terms of eigenvalues, this is an equality. Okay? Does that make sense? Is it clear that in terms of eigenvalues it's an equality? So if I looked at two bands, at s orbitals at 1a induced in G, and p orbitals at 1a induced in G, I'll have this set of eigenvalues together, yeah? And if I look at p induced at 1b and s induced at 1b, I'll have this set of eigenvalues together, but they're the same. They might have a different order energetically, but this theory knows nothing about the energy, so the set of eigenvalues is the same, yeah? 2 plus is 2 minuses, and 2 plus is 2 minuses, yeah? And or plus minus at 0, plus minus at 0, plus minus at 0, plus minus at 0. So this is the phenomenon of sp hybridization. This is the chemistry of sp hybridization. Which we'll understand from the Berry phase perspective. So that thing is telling you that if I take an s orbital at the 1a position and a p orbital at 1a position, I can separate them, okay, and move them by sp hybridization to having an s orbital at the 1b position and a p orbital at the 1b position. Yes? Okay. So by contrast, if I had two s orbitals at the 1a position, there's no way I could split them to move that to a 1b position. Okay? So there's no such thing as SS hybridization. Okay? So let me just get the more. So how do you see that? Well, that's very easy. So that's very easy to see because if I had S at 1a plus S at 1a, so 2s at 1a induced into the space group. This is a band formed by two s orbitals at the 1a Wyckoff position. This guy would have what eigenvalues in momentum space? Plus, plus, so 0 pi, plus, plus, and plus, plus, 2s. Okay? So this can obviously, just by eigenvalues, never be identical to, s at 1b plus s at 1b. Right? You can see it. It would have different eigenvalues. Yeah? This would be plus, minus, plus, minus. Okay? Does that make sense? Same thing with 2p orbitals at 1a, etc. So that's why S and P hybridization works, and SS doesn't work. Okay? So this is so this is one thing. And from this type of argument, you can figure out the Wilson loop or the Berry phase structure of these phases, which will be important in identifying the topological phases as I go to 2 dimensions. Let me give you a crash course on Berry phases. So what Jen said is that the Berry phase is basically equal, or the eigenvalues of the Berry phase, the eigenvalues of the Wilson loop, the log of the eigenvalues, is basically equal to the center of charge by Vanderbilt. This was Vanderbilt. Vanderbilt, Reza, many other people after. Vanderbilt. Okay, do you remember the statement? Roughly? Okay. So this statement comes from, you take the position operator, you project it into the occupied bands, you take it to the nx power, where nx is the number of sites in the x direction, and this becomes e to the I a dk ax dkx integral path ordered. Okay, this is a very simple calculation that you can do. Okay, take the position operator, project it into the whatever bands you want. So if I want just this band, I project it just into this band. If I want just this band, any set of bands you want, take it to the nx power number of sites, and this is the path order of the exponential of the Berry phase. Well, yeah, so to have a projector that doesn't jump, you'd have to be isolated. So it's a set of bands that is gapped from, but any set of bands is gapped from any other. So does this make sense? Mm-hmm. So this is PXP. This is the position operator. So let's write it down. Position operator on the lattice. So this statement made by Jen, that Berry phase is the center of charge, is proved like this. Yeah, yeah. So this is the position operator. So I take x is sum over lattice sites, j, e to the I 2 pi j over n, x, number of sites, nx is number of sites in the x direction. Okay, and I put this so that I put it to the exponential so that this is invariant under, it's got periodic boundary conditions. Otherwise, you'd have, okay, so this is Cj dagger 0, Cj, 0, Cj. And if I have more orbitals, I put an orbital here. Okay, so this is the position operator. And P is the projection operator into some set of bands. So you solve the Hamiltonian, you diagonalize it, you get the Hamiltonian to be, En at momentum k or whatever, gamma n at momentum k dagger gamma n k. These are the creation annihilation operators of your bands. And the projection operator into whatever set of bands you want is sum over n, which is the set of bands that you want. You can't have all the bands here because then it will be complete. Set of bands you want. Well, I mean, you can have, but it's true. Gamma n dagger 0, 0, gamma n, okay, at some momentum k and some over all momentum if you want. No, it is, but not if I pick a smaller set of bands than the full set of bands of the Hamiltonian, then it's not. If I pick all the bands, then it is, but that means I'm just filling all the bands of the Hamiltonian. But I can pick, this is the projector I can project in any, so I'm trying to find the center of charge of some bands. Yeah? Okay, any more questions? Did I answer your question? Yeah. Okay. Any more questions? Okay. So we're going to find the eigenvalues of this operator for these atomic limits. Okay, so let's find them. Let me erase this. So what we said is physically, I mean, of course you can compute this mathematically, but we're just going to find them physically. What we said is that Berry phase, or, lambda is e to the I theta. This is Berry phase, or integral of A. This is called the eigenvalue of the Wilson loop, whatever. Wilson loop. This is A dk. Okay, we said that these guys give you the center of charge. Yeah? We just said that they're the eigenvalues of the projected position operator. By Vanderbilt's theory, these guys give you the center of charge. Yes? Because you're looking, these guys are the, if I have the eigenvalue of these, I just have the eigenvalue of the position operator. So I know, so the Berry phase is really the eigenvalue of the position operator of the charge. Yeah? So if I have s orbital, if I have s orbital at 1a induced in the full space group, this is a band. It can look however you want to. Okay, it's some band. I claim that this band has a quantized Berry phase. Why? Well, I know where the center of charge, even though in momentum space, this looks like this guy in momentum space. This is in the Briand zone. Where does the center of charge sit of this band? It's induced from S at 1a. So where does it sit? So what is this theta? Yeah, I heard the right answer. So 0. So for this guy, Berry phase, I'm just going to always write e to the Berry phase, okay? Instead of just Berry phase. I'm going to write lambda is equal to what? E to the I0? Okay. Now, if I have P at 1a, lambda is equal to what? 1. S at 1b, lambda is equal to what? It sits in the middle of the unit cell. So what's this theta? 1/2 in units of 2 pi. So what is this? -1. P at 1b induced in G. What is this guy? -1 also. Very good. Okay, so now we have, for separate bands, we have this. If I formed a projector into these bands, I would get a Berry phase 1. And you can compute it and get this. Yeah? But now I pose to you the following question. What do I have if I formed a projector into 2 bands formed by 2 s orbitals at 1a? Okay? I'm going to get 2 centers of charge because I have 2 bands. Yeah? So this projector is 2 by 2. I have 2 centers of charge. What are these centers of charge going to be? Huh? So they sit both at 1a. What are they? 0 and? They're both 0 because they sit at 1a. So what are the Berry phases? Lambda 1 is equal to 1. There's 2. Lambda 2 is equal to 2. This matrix would be 2 by 2. It would have 2 eigenvalues. Sorry, it's equal to 1. It's equal, a unitary matrix has yeah. Okay? Yeah? Okay. So same thing for P, S for P at 1b plus S plus P at 1b. Okay? This would be equal induced, or sorry, P at 1a plus P at 1 plus 2 P orbitals at 1a induced into G would be -1, -1. Right? -1, -1 in terms of Berry phases. Yeah? Okay. Doesn't matter. I get n orbitals sitting at n s orbitals sitting at 1a. Yeah? They're going to have n eigenvalues 1. Yeah? You agree? Because they're just sitting there. Now, the fundamental difference is when you have s and p orbitals. So now you know how to compute the Berry phase for any amount of s orbitals sitting at 1a, for any amount of p orbitals sitting at 1a. Sorry, this is 1b. Sitting at 1b is -1, -1. P at 1a plus p at 1a induced into G. This is +1, +1, etc. Yeah? So you know how to, you just count how many orbitals you sit at which center of charge, and you put the center of charge. This is center of charge pi, or 1/2 in units of 2 pi, and e to the pi. Okay, so you know. So now the tricky part comes with when you have s at 1a and p at 1a. What do you think the eigenvalues of this guy are? The Wilson loop eigenvalues. So if I would have, so this means I would have a band, no matter what your model is. So you notice I'm not writing any type binding model. No matter what your model is, if I have bands induced by these orbitals from this Wyckoff position, what would be their Berry phase? Right, so these bands induced by orbitals in the Brion zone would have some, they'd look like something like this as a function of kx, okay, something like this, whatever. Don't care, and I take the Berry phase in this direction. It's got 2 eigenvalues, because 2 bands. What would the eigenvalues be? So what would it say? What would you say that they would be from here? Plus would give you what? if I have S1A. So S1A is localized at the A position. So what would be center of charge? So center of charge 0, e to the 0, 1. Yeah, so eigenvalue 1. What's P? So lambda 1 is equal to P. This would be the Wilson loop eigenvalue or the Berry phase. What would be the P? Lambda 2 is equal to 1. Okay? So you'd say, oh, well, there's no difference between this and this, for example, 2 S's at 1A. But that's not true, because that's stable. In other words, you cannot move by, I add more terms. So I take my Hamiltonian, I add more terms to the Hamiltonian. These have to sit here. They're quantized here, because the S orbitals sit here. But if I have an SMP at 0, SP hybridization can move my orbital, as we've just talked, away from, I have an SMP orbital, so I have an S and this guy here. And then SNP hybridization can move my orbital away from this point here, okay, by just introducing terms into the Hamiltonian. It can move it, move it, move it until I bring SNP to be here because of this identity. A band from S orbitals at 1A plus a band from P orbitals at 1A is equal to a band of S orbitals at 1B plus a band of P orbitals at 1B. So this is just the chemistry of hybridization. Yeah? So that means that by introducing terms into the Hamiltonian, I'm able to move these centers of charge of S and P orbitals from here to some position that's arbitrary. And this position is some theta, right? It's 1 over 130 of the unit cell, or square root of 3 over 5 of the unit cell, whatever, continuously. I'm able to move it from here to here. Yeah? So then these guys can move, the generic statement is that these guys can move to lambda, lambda star. So the Berry phases are e to the I theta, e to the minus I theta, and this is just inversion symmetry, right? If I have 1 theta, I'll have the minus theta. Okay, questions? Because they feel there's like a lot of, well, either this is too boring or too, just some life, please.
When you hybridize the SNP, you get you get two orbitals, right? The two centers of charge. So which one?
Right. So I had SMP here.
Yeah.
So I had 2 orbitals at the 1A Wicker position. And then I'll have 2 centers of charges, one SP hybridized orbital that will look like this sitting here, and the other one sitting at its inversion symmetric. So that's the only, so I can only do it with 2 orbitals, starting with 2 orbitals, because then to move them away from this 1A to 1B, I need to have 2 of them. And I can only do it with SMP, because otherwise I know that with SMP I can go from 1A to 1B. But with just S, if I just had 2 S's, just going two S's would be plus, 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 plus. And going to 1B would have plus, minus, plus, minus. So I can't do it with 2 S's. I can't do it like with anything else. So that's why only SMP hybridization exists. Thank you. Yes, there was another question.
So, this is for one-dimensional representations. How about two-dimensional? Example 2.
Yeah, I mean, this is for the simplest. Like, this is clearly for the simplest. But it's just here. This one is not going to be a 1 by 1 matrix. That's the only difference. That this is just so the 2-dimensional representations of the site symmetry group come here. You see, this is a 1 by 1 matrix. You just change it to 2 by 2.
I'm surprised it's that simple, because they don't necessarily, all these elements don't compute with translation.
Well, when you add it in momentum space, the only thing that translations will give you is the e to the ikx factor to all of them. Right. But in general, it doesn't matter. You can add, right, you can add to this. There's an ambiguity to, you can compute matrix elements of inversion here, which I am doing here in the momentum space, trying to find a representation of inversion. Or I can put inversion times any factor, but they'll all get an e to the ik factor. Thank you. Yes? Yeah, so you see 1, 1 is not, doesn't conflict with lambda, lambda star, right? 1, 1 is just one particular lambda, lambda star, right? So for some values of the, so what I know is that for some values of the Hamiltonian, if I fine tune them, especially if I have no hopping, say, SMP orbitals here, I can have 1, 1. But then what they'll do is, as I tune the Hamiltonian, the Berry phases will move because the orbitals are allowed to move. The Berry phase is the center of charge. If the orbitals are allowed to move, the Berry phase will track this movement. So I know that if I have SMP, I know that SMP here, one s orbital and one p orbital here, is identical as a band representation with one s orbital and one p orbital here. And the way it's identical is by sp hybridizing and moving away. So then I know that 1, 1, 1 here, if they come from S and P, so you can't just know only the eigenvalues, right? You have to. So if they come from S and P, the SMP here, you have to know where they are too. So I know that SMP here can hybridize and move here. So then I know that at some point they're going to have some position which is continuous between here and 1/2 theta, and this is this theta, right? So it's so generically these are the Berry phases. This is this theta. It's just some position in between 0 and 1/2, right? Does that make sense? Very good. Yes. It's not a Berry phase of a site. It's the Berry phase of the band induced from orbitals at that site. So in other words, these are s orbitals at all the sites in the lattice, right? So let me give you an example of a band, right? So I didn't write Hamiltonians because this is kind of like the conceptual thing. I don't want to write Hamiltonians, okay? So if I have a band induced by s orbitals at site 1a, okay, that band is if I wanted to write a Hamiltonian, the simplest Hamiltonian is T Ci dagger Ci plus 1, sum over I, which would give you this band, and you'd compute the Berry phase of that band. These are all bands. They're not just one side. This orbital is repeated everywhere. And this is the band that's induced by orbitals at this Wyckoff position at 1a. Okay? If I wanted to induce something from 1b, I would write, well, in this case, it would just be a change of origin. But for example, Jen's SSH chain, which was, this was, in that case, it was 2 sites per unit cell, I think, if I remember correctly. But 2 sites per, it's 2 orbitals per site. Okay, so you go between this and this. And this is one Wyckoff position, this is the other. So you go, or this is one, this is the other, mid here. So you go between having this strength and this 0 to this large and this 0. But basically, these are not just Berry phases, certainly not Berry phases of sites. They're Berry phases of the full band induced from orbitals at that site. Exactly, but the point is it doesn't matter. All this K integration does not matter. In the end, it's pinned by symmetry. Okay, so you can take your most complicated Hamiltonian, introduce a 1,000th neighbor, as long as you keep it fixed, right? As long as you don't have long, say some finite range hopping, a 1,000th neighbor hopping. Build whatever Hamiltonian you want to. Okay, with localized orbitals at sites, introduce some hoppings. You're going to get these Berry phases. There's no way around it. They're pinned by symmetry. Does that make sense?
So the implication of this, I guess, is that I don't have to worry about doing integrals. I'm just looking at boundaries of my Riemann zone.
That's right. For the cases where you have symmetry, things simplify considerably. Yes. So in this case, you don't need to do any integrals. So yeah. So that's okay. So now, so this is what I wanted to. Let's say maybe we end for like well, not end, but like take a 3-minute break. But I wanted to show you. I wanted to find, to see if we can find what the Berry phases of this representation, the Briand zone, is. So I'm always going to go in the end to the Briand zone, because that's that's how in the end for one-body physics the Briand zone is more efficient, but I want to know in the Briand zone if I have momentum 0 and pi and I have bands. So we're going to do an exercise. So if I have bands that have eigenvalues plus, plus, minus, minus, plus, minus, minus, plus, 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 minus, minus. Okay? So I have these bands. I have 6 bands below the Fermi level. Okay? And I have, these are the eigenvalues in the Briand zone under inversion symmetry. What are the Berry phases? Okay? So how would you go about this exercise? Well, let's just go slowly. So this band here, okay, first of all, consider them decoupled. Okay? This band here, and they, you know, in 1D they are decoupled actually. This band here is an s orbital at 1b Wick opposition. You can see it here, right? Yeah? This is the s orbital at 1b Wick opposition induced into the symmetry group. And for the next lecture, I'm going to kill this induced, you know, this sign, because it's, this is an s orbital. This is what? What is this band? Huh? Same. Okay? What are the eigenvalues? What are the Berry phase eigenvalues of this guy? The lambdas. They're at 1b Wick opposition. So they're at the center of charge is at 1/2. And they're 2 s's. So you know they can't move from there. -1 and perfect. Now, what are these 2 guys? By there. S at and P at 1b. Yes? Induced into G. Okay? So what are their Berry phase eigenvalues of these 2 guys? Of these, both of them? They're at 1b, but from 1b I can move them to 1a because they're S and P. So generically, what are they going to be? So these are, you agree that this is S at 1b and P at 1b, right? Because you can see it here, S at 1b and P at 1b, right? They're at 1b, so you would say that their eigenvalues are -1, -1. But they're S and P, so they can hybridize. So generically, for the most generic Hamiltonian, I'm not going to get -1 and -1. I'm going to get what? Lambda, lambda star. Lambda 1 and lambda 1 star. And okay? What is this guy, though? S1a, P1a, induced into G. What are its eigenvalues? Another lambda. It doesn't have to be the same as this lambda. Lambda, lambda star. So this is a system formed by 2 s orbitals at 1b and S and P 2 s orbitals, sorry, an S and P orbital at 1b, which can hybridize, sp hybridization, and an S and P orbital at 1a, which can also hybridize. So it's a system formed by 2 hybridized S and P orbitals and 2 s orbitals at 1b. Yeah? So this Wilson loop, its Berry phase eigenvalues are -1, -1, lambda 1, lambda 1 star, lambda 2, lambda 2 star. Okay? So from now on, if you have any type of inversion eigenvalues at 0 and pi, you'll be able to tell me, in 1 dimension at least, what are his Berry phase eigenvalues, generically. Okay? Is that clear? So that's, okay. So then we're just going to go to 2D and figure out how to find, you know, using this method of elementary band representation, the topological, the topological phases. So what do we do in the schedule? Take a 5. Any questions? Yes. So the high symmetry points depends on which group you have. So for inversion, in 1D Briand zone, there's only 2 high symmetry points, 0 and pi. Generically, you'd have to find these eigenvalues for every k that's left invariant under some h. Okay? And there's a set of, and there's some extra work. So you ask, you know, what's the minimal set of k's that tells me all the eigenvalues in the Briand zone, right? Yeah. And that's called the maximal k vectors. The maximal K vectors are tabulated also on the Bilbao crystallographic server, and it's the set of, so if you want to find out just the eigenvalue structure of this band representation at every point in the Briand zone, so then you have to have this term leaving this point invariant. But it turns out that you don't need to look around all the Briand zone. You only need to look around a set of finite maximal K vectors, and that gives you all the eigenvalue structure around the Briand zone. Does that make sense? Yeah. Okay. Yes?
So you have 6 representation here.
Here I have 6 bands that I focused on.
Why do you have 2 separate?
I don't have 2 separate. You know, I could have mixed these around. Okay, so let's say I have the following. Let's say I mix these around. So let's say I move this one, and well, if I move this one and move it here, nothing changed. But let's say I move this one and move it here. Okay. Now I have plus minus, okay. Plus minus minus. Hang on one second. Plus minus plus. Yeah. I just moved this eigenvalue here. Just by my Hamiltonian does some, you know, I just change some terms in the Hamiltonian. Plus minus minus minus. Yeah. This change. Okay. Well, I would ask you, you know, what is this guy? Well, you can say S at 1b, S at 1b, S at 1a, P at 1a, S at 1, P at 1b. Sorry, shit. S at 1b, P at 1a. Right. Hang on. There's some. I did something wrong. 1 second. Plus minus minus S at 1a. What? Yeah, this is not P at 1a. This is P at 1b. Yeah? Okay, so then it's the same. Okay? I look at these orbitals, and I see S and P. It doesn't matter where they sit, right? I see S at 1a and P at 1a. These can hybridize. I look at these orbitals, I see S at 1b and P at 1b. This can hybridize, so this will give you lambda star 1, lambda 2 star. Generically, they always will, because generically you're going to have some term whether they hybridize fully, so they go to the other side, to the, you know, from 1a to 1b. You don't know. That depends on the energetics of your Hamiltonian. But generically, you're always going to have some terms around that do this, right? So what we're asking is for universal statements, not for fine-tune. So the universal statement is that these hybridize, these cannot, because they remain with 2 s's. So the eigenvalues will be -1, they're at 1b, -1, lambda star, lambda star. Does that make sense? So by this, you can now, whatever eigenvalues you have, you just take them 1 by 1 if you want. Here I took them just to confuse you, 1 by 1 and 2 by 2. But you can take them 1 by 1 and figure out the Wilson loop structure. Does that make sense? Any other?
Okay,
Is it possible to what? I mean, if I have 3 orbitals, I could have, you know, is it possible for 3 orbitals to hybridize together? Yeah, sure. It's possible for any type of, you know, you have SD hybridization. I can have some other. So it's possible that sometimes hybridization really means that I have some things on some set of orbitals on one site, and I can move them to another site. Okay. Now here I need S and P. You see, I can't do it with 2 s's. But as far as I know, there's no, I don't know, there's no, you know, I could have 3 orbitals on one site and could move them away only if there's 3, but not 2. In that case, it would be your, I don't see any I don't actually, it's easy to check, but I don't know any obstruction to that. Yes? Sorry. Yes? The meaning of the arrows is just these H's have to belong to G. H is a group, H is an element of the space group, because you're trying to compute the space group representation, which is induced from the point group representation. So we're trying to compute, you see, we're trying to compute this induced from representations of sites. Yeah? So these belong to the space group. These belong to the point group, which is the site symmetry group. See, this is only defined as a representation of the site symmetry group. So these have to belong to the site symmetry group. These have to belong to the space group, much larger set of these than of these.
What's the call with induction in terms of compatibility?
So it turns out that so normally there are two separate things, but it turns out that this induction contains enough information to give you all the compatibility relations if you want to. It's kind of a strange thing that's not really understood, but usually they would be totally two separate things. So for example, in higher dimensions, say I would go to like 4D groups. I don't know if that's true. In 3 dimensions and 2 dimensions, these inductions from atomic orbitals contain enough information for you to be able to obtain all the compatibility relations. But I don't know if that's true in higher dimensions, for example.